Welcome to Almost Here, Round the Corner Future Technology podcasts with Richard Jacobs. Future technologies poised to transform our lives for better or worse are the focus of this podcast. Almost here means these technologies are now here and starting to be used, or just around the corner, from Bitcoin to artificial intelligence, 3D printing, blockchain, virtual reality, and more. Coming to Dallas, Texas, September 14th, 15th, and 16th, 2018, the Blockchain and Future Tech Expo. This is going to be a gigantic conference of over 5,000 people. We're going to be talking about blockchain and its applications. We're going to be talking about quantum computing, cybersecurity, artificial intelligence, and several other future technologies that are poised to and actually changing our lives as we speak. Here's why you should attend. As you may know, early adopters are the ones that investigated and profited from things like the gold rush in the 1800s, from the dot-com boom in the 1990s, from the internet boom in 2005, from the smartphone explosion in 2007, from the real estate boom that ended in 2008, and of course, from the Bitcoin boom that started in 2012. Early adopters act now. They don't wait till later. They go out west first. In their covered wagons, they find the biggest gold nuggets. If you consider yourself an early adopter and you want to find the biggest nuggets, then you owe it to yourself to attend this upcoming conference. Blockchain is going to affect how we control and store our medical data, how we send money around the world, how we bank, and more. But artificial intelligence, quantum computing, and cybersecurity will play a pivotal role in our lives as well. And that's why our next event, September 14th to the 16th at the Dallas Convention Center, is going to have not only 5,000 plus attendees, but will showcase blockchain, AI, cybersecurity, quantum computing, and more. You want to get in on the coming gold rush of future tech and opportunity as an early adopter. Don't be left out. To register, go to bftexpo.com. That's blockchainfuturetechexpo.com. Thank you. Hey, this is Richard Jacobs with Future Tech Podcast. My guests today are Andy Kieatiwong, the CEO, and Reiley Weeks, the CSO, Chief Science Officer of Arc Engines. How you guys doing?
We're doing well. How about yourself? Great. Thanks for having us.
Yeah, thanks for coming. So, I always start off with the basics. What is Arc Engines? What's the premise of it?
So, Arc Engines is a manufacturer and designer of rocket engines and propulsion systems for both launch vehicles and satellites. So, we utilize 3D printing and what's called design for additive manufacturing to optimize and enhance the performance of these propulsion systems.
So is the 3D printing that you're doing here on Earth? Because I've heard that now what people would like to do is have 3D printers up in space, so spaceships and everything could make tools for themselves and other things while they're up there in space.
Yeah, definitely. Our printing is here on Earth. We use industry standard metal printing technologies to create our systems. But I do know what you're talking about. There are companies like Made in Space. They have a 3D printer on the International Space Station, and that's definitely what the trend is. When I worked at SpaceX, I've heard instructions given to the 3D printing missions from Elon that we want to get this. To be working on Mars, do what you have to do that. So that's definitely something that we've seen many companies trying to do, especially for asteroid mining companies. Whenever they mine the raw materials, they don't want to bring back all of that to Earth. It's more efficient if they had these metal printing machines that could take their raw resources and turn them into usable items. So yeah, you kind of hit the nail straight on the head. With additive manufacturing.
Well, I talked to Made in Space and I forget the name of the asteroid mining company, but Planetary Resources. So I've spoke to a few. That's why I asked for the distinction. So
exactly.
I'm sure weight is like probably the biggest factor. I'm sure 3D printing you get much better efficiencies, and this is not usually mass production. So if you're making one rocket that's going to go to Mars, you don't need to make a million of these of an engine. So I guess 3D printing is probably ideal for this kind of application, right?
Yeah. So you mentioned 3D printing helping to reduce weight, and that's absolutely true and aid on efficiencies. And to kind of burrow into that a little bit more, 3D printing allows us to optimize geometries using sort of a biomimetic design process. So the internal geometries of the engine are far more efficient and actually mimic those found in nature, blood vessels and things like that. And so that's really where, that's really where the 3D printing shines, is the ability to make those sorts of geometries, because standard subtractive techniques cannot get the smooth curves or the complex shapes that 3D printing can.
Well, all right. So you said biomimicry. That's really cool. I don't know of any jet engines in nature, but you mentioned blood cells. So where did you guys look to for inspiration, biomimicry-wise? What systems in nature do you see that are amazing at propelling things?
Oh, so it's a great question. Our reference isn't so much nature propelling things, but nature moving fluid. So if you look at the human circulatory system, it's an incredibly efficient method of transporting a fluid from one central point, the heart, to a bunch of points all over the body with very minimal energy requirements. There's very little turbulence in the actual flow, and it does it very efficiently for hundreds of years without much of an issue, right? For 100 years, I guess, without much of an issue. And so looking at that and the ability to go from one central point, the heart, and branching out in a smooth fashion, that's where a lot of our designs come from. So in the rocket engine, you have your single inlet, but you need to for propellant, but you need to branch that out to multiple outlets at the actual injector face for combustion. And so we modeled our passages off of this sort of circulatory system branching pattern to create an efficient method of distributing the fluid.
Also, for combustion efficiency and completeness, that's why you wouldn't just blast everything out through one huge hole. You'd want to send it out through a whole bunch of smaller holes, I guess.
Exactly.
Roughly.
Yeah.
So, how did you know that the human body moves blood around efficiently? Like, I'm just curious about that. Like, what tells you, or what does literature say that shows people that it's so efficient?
So from the literature itself, I couldn't point you to anything exactly, but we performed simulations that are on similar passages, the same sort of fractally branching passages, and found that using that shape, the fluid flow was just far more efficient. There's very little head loss, very little energy loss in moving fluid from one point to another following those sorts of shapes. We found that time and time again through various fluid mechanics simulations.
Well, can you give me an idea of the scale? Like, how much more efficient is the human body at moving blood around versus, doing it with, pipes and emulating that system, let's say?
Another good question. We found our comparison is more towards injector plates. We haven't done the full human body simulation. That's a little outside of our abilities. Sure. But our investigation, we see about a 70% improvement in efficiency following the human body pattern. Yeah,
that's a lot.
Yeah, it's.
What is it about the inside radius, the inside features of a blood cell that make it efficient at transporting the blood, or what is it that's doing it? What does it look like?
So it's the vasculature itself. For what we're looking at, the blood cells themselves are insignificant to the overall flow. But what is significant is how smooth the veins, arteries, etc. move. So every time that they need to make a turn in the body to go to a different direction, those turns are very smooth and there's no sharp corners. And when branching occurs, that is also done in a very smooth fashion, so that there's no sudden changes causing the flow to kick into a higher energy regime, losing energy to the flow.
And to give you a better idea of what the current state of the art is, these injectors, combustion chambers, they are machined. Traditionally, they need to create engines that take into account what angles a drill bit fit into their components, or would it be able to fit on a lathe. So you get a lot of 9-degree angles, a lot of sharp angles that actually inhibit fluid flow and create a lot of turbulence, therefore a lot of energy loss. So following the design that Reiley just mentioned, we're able to greatly reduce the pressure differential across our inlet and outlets.
So is most of the efficiency gain at these bends and curves and splits, or what about the straightaways? Is there anything in blood cells that makes it more efficient on the straightaways?
Not necessarily. At least nothing that I know of. It's definitely most significant at the branches and at the curves.
Okay, I didn't know if like there's ribbing or something, inside of the blood vessel
Yeah.
that maybe makes it more laminar or something.
I understand. Yeah. As far as I know, the straightaways would be the same.
Not that there are straightaways in the engine.
Yeah. True.
Well, kind of, but yeah. Okay, I gotcha. So, all right. So you're looking to make engines for what kind of rockets? Like, who are your customers specifically?
So our engines that we create, basically it's fuel agnostic and thrust agnostic. So we could create rocket engines for both launch vehicles and satellites. So there are two different types of rocket engines or rocket propulsion systems. There are solid rockets and then there are liquid rockets. So we focus more on the liquid rocket side. We're using both monopropellant engines and bipropellant engines. So that gives us the ability to create engines ranging from millinewtons of thrust all the way to upwards of 40 to 50,000 pounds of thrust. So on the upper end, we could create engines that are half the thrust of a SpaceX Merlin engine. So that kind of idea of what kind of platforms we could service.
Okay, very interesting. So you're getting a lot better efficiency with the flow of the fluid. What kind of metrics, what kind of results is that giving you? How much more output per pound are you getting through your engines, or how would you characterize how much better your stuff is versus what's out there?
So in overall, we're able to dramatically change the shape of the engine and the internal passageways to the point where we're able to also greatly reduce the part count on a system. So overall, with our efficiencies in terms of fluid flow and heat transfer abilities, our systems come out at upwards of half the weight of traditional systems.
Huh. Wow, that's pretty significant.
Yeah. When you when you get rid of a lot of unnecessary nuts and bolts and gaskets, that really brings down your weight.
So it's half the weight, and then what other characteristics are improved? Combustion efficiency because of the geometry, or what else?
Correct. Combustion efficiency, but also we're able to have a cascading benefit throughout the whole system because, like Reiley said, we have a upwards of a 70% reduction in energy loss in our engines. That means that we need less energy to move the same amount of fuel mass. So upstream of the engine, we could downsize the valves and the turbopumps and the tanks so that we could theoretically lower the weight of the entire system even more. And that's all stemming from basically the heart of the rocket inside the motor and the engine. So
what when it comes to going into space, I'm sure every ounce matters tremendously. Like, how important is it to reduce weight and to be able to make things more efficient?
It's pretty much the number one priority. I mean, if you look at one of my favorite examples is on the space shuttle. The original space shuttle, that huge tank that is attached to, everyone knows it as orange or like a sort of an off brown, that used to be painted white. Well, they realized that if they just didn't paint it, just paint, they would be able to save 200 kilograms, and that was worth every cent. Sure. So, I mean, on a space shuttle, that thing is huge. It's massive, but 200 kilograms, and they did it. So every pound, every ounce matters. It's behind the safety of the payload. That's pretty much the number one priority, is making things as light and efficient as possible.
Yes, and essentially for every kilogram that you eliminate from the engine, that's either another kilogram of fuel or another CubeSat that you could have in your payload. So weight really does matter in these systems.
Well, do you have any metrics, that come from NASA or whoever, like it's, $100,000 per kilogram or something saved, or anything like that?
Yeah, so for CubeSats, it costs anywhere between, depending on the service provider, anywhere from $40,000 to $80,000 to launch one unit CubeSat into low Earth orbit. So regarding their launch vehicle companies like SpaceX, they're trying to get the price per pound to be below what, 10,000, or was it 1,000? Am I missing a zero there?
I'm not sure. I don't remember off the top of my head.
Yeah,
Around there. Yeah.
So if for us, being able to reduce the weight of the propulsion system, especially for small launch vehicles, that could mean increasing the margins of our launch service providing customers by 20 to 30%.
Oh, okay. All right, very good. And that could translate to, I mean, per launch, what's your guess on what that could translate to in savings?
Per launch, I mean, it could. So there are multiple facets for lowering the cost for a launch vehicle service providers. In terms of manufacturing, basically the manufacturing cost gets cut in half for these engines, but also since they are more lightweight, it provides them a greater opportunity to have more payload onto the system. So it depends. Of course, it varies per launch, but per launch for say a rocket class the size of Electron rocket, it could theoretically increase their margins by a few $100,000.
Okay, very good. Are there any launches that wouldn't be possible or that will now be possible because of your efficiencies that you're going to bring?
So yeah, there are actually two main types of vehicle platforms that could deliver systems into space. There's your classical rocket, your bipod rocket that goes up and then angles, and then there's the hypersonic vehicles that are air breathing and go at very high speeds to get into space. So for us, we are actually helping to enable these hypersonic technologies to come online regarding fuel injection and engine cooling. With our geometries, we could create we could actually create the systems that are needed for some of these hypersonic vehicles to survive Mach 6 and beyond. So that's where I say where we're enabling technology. For us, we're just getting started with our IP. I mean, there are things that we're able to create that enables a rocket engine to do things that it can't do today, such as ignition, very deep throttling, and durability. So that's in a nutshell, without me angering my CTO, what I could say about us enabling different tech.
Oh, well, the ones you mentioned, what is deep throttling and what are some of the other, why is it important to go Mach 6 or above?
Okay, that's an interesting question. I'll start with the deep throttling. Throttling is just essentially running the engine at a point that's not its intended high efficiency design point. So most engines operate around their 100% throttle range, which is maximum thrust, maximum flow rate through the engine. Deep throttling is throttling down to very low percentages of its design point thrust. To get the exact point where deep throttling starts, I think it's around 20% of maximum efficiency. But being able to throttle that low allows you to have a greater variety in mission and payload, and allows you to greater control the engine by being able to fluctuate that engine to just the right thrust required. Because if all of your engines operate exactly at 100%, you really need things to go just right, and control becomes some issue.
Right. If you could think
it's like having a race car where it's like having a car or a race car where you can only floor it. You can't gently move forward or backwards.
Yeah. It's okay. You can only floor it. It gets really tricky when you're trying to park.
So yeah,
exactly. Okay.
When you try to imagine what kind of vehicles that these very low deep throttle engines enable, if you could imagine any spaceship or vehicle from a science fiction game or film, that's pretty much what these engines will be able to do.
Yeah, where you see them all having the main engines, but they're able to just kind of creep up and steady and dock with some port or land on some rock floating in space. that's all enabled by deep throttling.
Okay, wow. And then what about the Mach 6 threshold? Why do you need to go even faster than that, or that speed?
So for launch vehicles, they need to attain a certain delta V in order to achieve orbit, low Earth orbit at least. And the way hypersonic vehicles that want to launch payloads into orbit, how they work is that they utilize the oxygen in the atmosphere in order to enrich their fuel burning process. Typically, for normal launch vehicles, they bring their fuel and oxidizer with them on the vehicle. For hypersonic vehicles, they need to go at such high speeds and utilize the oxygen in the air to enrich the fuel combustion within their engines. So they don't carry any oxidizer with them. So that's why they need to go at such high Mach numbers to obtain the delta V needed to launch their payloads into space, but also to collect enough oxidizer to sustain the burn of their very powerful engines. So that's why these vehicles need to travel super fast.
Changes when you go that fast?
Exactly. yeah. That's exactly my point. At those speeds, I think I've heard an engineer friend of mine described it as at those speeds, it's like trying to run through Jello. Just the skin friction of the air along the vehicle is so great. You get intense heating. And then the engine itself, those same high speeds cause huge amounts of thermal energy buildup. So that's where a lot of our technology comes in, to build the ability to cool the engines while they're operating at insane temperatures, and be able to cool the body even while operating at insane temperatures is where we're trying to go with this in terms of hypersonic vehicles, at least in part.
What's the fastest hypersonic vehicle that's ever been created or used? Just out of curiosity.
That information.
Probably classified. Yeah, I don't know what's
really?
fast. I have a favorite though.
Yeah.
Oh yeah, the Blackbird,
the SR-71.
It's a beauty.
Did they publish the max speeds on that? And I heard
they published a max speed, but they don't know what the max speed is because they never found it. The engines on that thing.
What was it? Out of curiosity.
Yeah, it was around Mach 3, I believe.
That sounds pretty slow. I think it's higher than that.
You think? Maybe it's 3.5, but it's pretty quick. They were worried that the plane would fall apart before the engines themselves reach their max speed.
Could have pushed it.
Yeah. Probably, yeah.
And you're talking about going to Mach 6 and above.
Yeah.
Wow.
It's
well, that's what some of our customers are saying.
yeah, exactly. Yeah.
We just want to enable them.
Mm-hmm. If we can provide a piece of tech that'll give them there, more power to them.
Huh. Interesting. Okay. What kind of temperatures are developed at the skin of a rocket once it goes, Mach 1, 2, 3, 4, 5, 6? Any estimates there?
We need to bring in our CTO for that to answer that question.
Yeah. So the skin temperature.
Even ballparks, 1,000 degrees, 5,000.
Probably around 1,000 Kelvin at the really high Mach is probably a decent estimate, but I couldn't say for sure.
Okay. So where are you guys at production-wise? You just have concepts built? Have you actually made parts for engines that have flown and you've seen the performance increase? Is this at the wind tunnel stage? Like, where are you at with it?
Yeah, basically, if you imagine for planes and aircraft, we are in the wind tunnel stage with our rocket engines. So we've designed them, we've manufactured them, and we've tested a couple. We're actually gearing up for a big test this Saturday. But we're working towards getting more data on our engine and finding. We're currently in talks with certain launch vehicle and satellite companies to begin implementing our systems onto their platforms, so we can perform real world environment, suborbital or in space testing. So we're right there. We're about to go into space. We just have a lot of testing to do on the ground first, but we're beginning in the middle of those talks to do real environment testing.
That's cool. And that's going to happen, do you think, when? This year or next year?
So for us, the remainder of the ground test, we're looking to wrap it up towards the later end of this year. And then with the way our discussions are going now, we're looking towards sometime next year at the earliest for us to begin getting these systems up in the air and in space. And that's actually a very quick timeline for space companies. But we're luckily for us in our design, manufacturing, and test methods, we're able to rapidly go through this process.
What about for regular commercial airliners? I know you can't do everything, but is there any chance to license your technology to improve their engines so they can cut weight and be more efficient?
Yeah. So for other types of engines, you're talking about bypass engines, turbojet engines using compressors and turbine blades. So for our technology, basically we boiled down the rocket engine to its core functionalities, which is moving fluid and heat around and shaving weight wherever we can while maintaining a certain safety factor. So when you boil it down, our IP can actually benefit any high-performing system that has critical heat or critical fluid flow, and you find that in a turbojet engine, bypass engine. So yes, to answer your question, we can license our technology to improve certain components, such as a turbine blade with cooling internally, or other areas inside the combustion section of the engine. We just, as a startup, as you know, we're maintaining our focus on the rocket engine part. But yes, in the long run, we're looking towards licensing our IP and tech to improve other systems outside the space industry.
Okay. All right. Very good. Any other interesting developments coming that you can comment on, or it's all, you gave me the generic plan and that's about all you can say?
Let's see what's exciting. We're bringing in our own metal printer soon. So far we've been contracting out our manufacturing, so we'll soon have a EOS M290 here on in our facility at UC San Diego. So that's exciting for us.
yeah, that's gonna be awesome. Wait for that.
I could have asked more about the printing itself. Can you do composite printing, or is it just the metal parts and then they need to be assembled, or what's the next gen in the metal printing itself?
Right. So that's a great question, and the way we shape our technology tree and patent portfolio is actually based on what we see on the horizon for metal 3D printing. So right now we see homogeneous materials that are able to be printed, and the main materials are aluminum, titanium, stainless steel, high nickel alloys. On the other upcoming, we see copper and niobium and some other exotic metals being able to be 3D printed. But further out, we see metal print technology such as functionally graded metals that can be printed. So this is, for example, you start your print off or one section of your wall with a copper for high heat transfer abilities, and then you slowly grade the copper to a different material, such as an Inconel high nickel alloy with really good strength properties. So we see that technology as up and coming in terms of metal printing, and we've based our technology and technology tree around what we see coming up. So we're pretty excited about the other metal printing technologies out there. And you mentioned earlier in this podcast, printing in space and off world. So zero gravity or microgravity printing is something we know is being worked on as well. So we see a lot of exciting developments coming up in this field.
An idea just occurred to me. I don't know if this is ridiculous, but is there any benefit to printing while moving? 3D printing at high speeds or something while you're moving. Would there be any benefit to that?
So there's
necessarily, because I don't think it would actually affect the print at all. It's as soon as you have a constant velocity, it all just becomes an inertial reference frame.
Yeah, it's all relative.
Right.
Are you talking about high speed as in you're in orbit, or are you here on Earth in a Concorde airplane going at high speeds and trying to print something?
Either. I don't know. Again, it just popped into my head. I know it would take thought to see if it's useful at all. It just popped in my head. That's all.
No. I see what I see what you mean, because we in our conversations, of course, with defense, they want to get metal printers out in the field, and it would make sense for them to look into technologies that enable them to have a good 3D print. For example, on board a carrier. When you're out there in the ocean, you see a lot of you imagine people getting seasick. Imagine these metal printers going up and down with all the waves and motion. So there are, and I know there's tech, and the Navy's been actually investing quite a bit of money into that kind of technology. 3D printing while in motion, whether aboard a ship or out in the field or going at high speed. So you actually hit on something pretty important, and that's the ease of metal or 3D printing in general, taking it wherever with you, not just in space, but here on Earth. So yeah, that's something that I almost forgot about, but something that we've definitely known about.
Yes, I guess stabilization would be really important.
Yeah, absolutely. In fact, one of the interesting things is looking at the different properties of each of the methods for printing and how they handle movement and changing orientation. For example, the print method that we use is called DMLS, direct metal laser sintering, and it essentially laying down thin layers of metal powder and using a laser to trace the pattern of the print out and slowly build up powder layers until you've melted out your piece. Now that is incredibly sensitive to vibration and movement, so it's probably not the kind of thing that you could easily put on a space station or an aircraft carrier, especially because it's highly reliant on gravity and accelerations remaining zero. Whereas the FDM printing, which is sort of the classic plastic printing that most people know about, those are really quite resilient to accelerations and changing in movement. So that's the kind of printing that is actually currently up on the International Space Station, and is probably the type of printing that will be best suited for the military move application because it's resilience to movement.
Yeah, it's funny. I had a picture in my mind of years ago in the movie Jackass, they were trying to tattoo one guy while they were driving off road in a Jeep. Anyway.
It's basically that with the powder printer, everything moving all over, and what you'd end up with is probably just a mess of gobbledygook and not your actual part.
Okay, well, very good. So what's the best way for interested parties to contact you?
So for interested parties, they could shoot us an email at info@arc-engines.com. That's info at arc-engines.com. Or they could give us a call at 858-869-9683. So that those two methods are the best way to contact us. So leave us a message. We're happy to talk to other parties, interested parties out there. We're all geeks at heart, so whether it be business-wise or technology-wise, we'd be happy to discuss.
All right, guys, well, that's great. Well, I appreciate you coming on the podcast.
Yeah, thanks for having us, Richard.
Yeah, thanks, Richard.
Coming to Dallas, Texas, September 14th, 15th, and 16th, 2018, the Blockchain and Future Tech Expo. This is going to be a gigantic conference of over 5,000 people. We're going to be talking about blockchain and its applications. We're going to be talking about quantum computing, cybersecurity, artificial intelligence, and several other future technologies that are poised to and actually changing our lives as we speak. Here's why you should attend. As you may know, early adopters are the ones that investigated and profited from things like the gold rush in the 1800s, from the dot-com boom in the 1990s, from the internet boom in 2005, from the smartphone explosion in 2007, from the real estate boom that ended in 2008, and of course, from the Bitcoin boom that started in 2012. Early adopters act now. They don't wait till later. They go out west first. In their covered wagons, they find the biggest gold nuggets. If you consider yourself an early adopter and you want to find the biggest nuggets, then you owe it to yourself to attend this upcoming conference. Blockchain is going to affect how we control and store our medical data, how we send money around the world, how we bank, and more. But artificial intelligence, quantum computing, and cybersecurity will play a pivotal role in our lives as well. And that's why our next event, September 14th to the 16th at the Dallas Convention Center, is going to have not only 5,000 plus attendees, but will showcase blockchain, AI, cybersecurity, quantum computing, and more. You want to get in on the coming gold rush of future tech and opportunity as an early adopter. Don't be left out. To register, go to bftexpo.com. That's blockchainfuturetechexpo.com. Thank you. You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.